Hey there, Patriots. In this video, we are going to take what we talked about with finding our binomial distributions and the probability of a binomial experiment being a success for a different number of trials, and we're going to expand on that idea. Today we're going to create histograms, we're going to compute the mean, and we are going to compute the standard deviation of that binomial distribution. So when we graph our binomial distribution, remember any probability we can represent in our graphic form. We are going to have R successes out of N trials. So what we're going to do is we're going to place our R value along our horizontal axis. So it'll be on the X. P of R, the probability of this many successes, will go along the vertical axis. So since it's a discrete probability, because our successes can be counted by whole numbers, so it is discrete. If it's not counted by whole numbers, it's continuous. Because we can have 0, 1, 2, 3, 4, 5, 6, 7 successes. We can make our histograms, and that's what we're going to do. Stop groaning. We're doing it. So to construct our histograms, make sure you put your R values on your horizontal axis. We're going to make our bars. Every bar in our histogram is going to be 1 unit wide, and we're going to put the middle of it over our R value. The probability, once we have figured it out, goes on my y-axis. It goes up. And just as a reminder, the heights of all the bars need to add up to 1 because that's all the probabilities that are happening. And then we're going to see this in class when we start to work. The heights of a different probability add up to 1.001 because of rounding. This is why I don't like to round as I work. I like to round at the very end. So literally, these are the steps that I just talked about. We're going to put our R values on our horizontal axis. We're going to put our probability that R is R on our vertical axis. Remember, R is the number of successes. We're going to make our bars. So with R right in the middle of every bar. So we're going to go half to the left. We're going to go half to the right. And when we make our histogram, it'll look something like this. So this, I titled it, remember, don't forget your titles. I titled this probability that R successes will occur for a binomial experiment. Here are my number of successes, 0, 1, 2, 3, and 4. And here's the probability that every success happens. So notice they touch each other. My bars are 1 unit wide. So this goes to negative. Can have negative successes, but negative half to half. Half to 1.5. 1.5 to 2.5, etc., etc., etc. But it's these number of successes is what I'm looking at. So please make sure you sketch that into your notes. Fun fact. Totally fun fact, because all the facts I give you are totally fun. If we have a probability of success is 1/2, when we make our histogram, it's always a normal curve. It is always a symmetrical distribution. So right in the middle, we go out from the ends, and that's we either call that a bell curve or we call it a normal curve. Because if we makes our bell curve, and that's because the probability of a success is half. Because then the probability of failure is also half, makes this a nice normal distribution. Pretty cool. Fun fact. We are also going to learn today to calculate our mean and our standard deviation. Remember, another word for mean, mu, the mean of a population, is my expected value. It is the expected number of successes that I am going to get. Little sigma is my standard deviation. It is the spread of the data from the mean. So it tells how far up or how far down we go from the mean. If you want to read all of this, go ahead and hit pause, and you can jot it down. But I gave you the down and dirty of it. So how are we going to compute our mean and our little sigma, our standard deviation? Awesome, glad you asked. So mean of a population is going to be n times p. The number of trials, the number of times I'm doing my experiment, times the probability that I get a success. Then my standard deviation, I am going to do n times p times q, the number of trials times the probability of success times the probability of failure. Take the square root of that product. That gives me my standard deviation. So remember, R is the random variable representing the number of successes I am looking for. R is not in either of these problems, but we have to ask ourselves, how many successes do we want to find the probability, to find that little p? Actually, we need that for the big P. N is going to be the number of total trials I do. P is the probability of success of a single trial. and Q is the probability of failure of a single trial. And of course, Q is going to be 1 minus success, because both the success and the failure have to add up to 1. All the probabilities have to add up to 1. We can use the formulas that we had put into Google Sheets. I wouldn't. I remember how much you hated that, so I would not put those into Google Sheets, but you could. These ones, these two formulas are only if we are using a binomial distribution. So then, when we have our spread, the further we get away from the mean, the more likely we are to run into our outliers. So Chebyshev's theorem, we did that way back in our first chapter, tells us that no matter what our distribution looks like, so it could be normal, it could be skewed to the left, it could be skewed to the right, and you're thinking you did that differently. No, remember, if we are skewed left, most of your data is on the right. The tail is on the left. If you are skewed to the right, most of your data is on your left, and the tail is on the right. So 95% of my data is always within 2 standard deviations of our mean. That's according to Chebyshev's theorem. We did that in chapter 1. So if we are outside of 2 standard deviations up or 2 standard deviations down, we're much less likely to happen. There's only a 0.25% chance that I'm going to be above or below those 2 standard deviations. So if we are more, general rule of thumb, if we are more or less than 2.5 standard deviations from the mean, we're probably an outlier. So go ahead and jot that down. So how are we going to find that? How are we going to find our unusual values? We're going to do mean plus 2.5 times our standard deviation, or we're going to do mean minus 2.5 times our standard deviations. This is how far up we can go and still be in my be expected to happen. If I'm above this number, I'm probably an outlier. If I'm below this number, I'm probably an outlier. All right, and then so we are going to do, so we can use this indicator to determine whether a number of successes is unusual, potentially an outlier. So we're going to look at this problem when we come into class tomorrow. So if you have any questions, I know this was quick and it was a lot of information. It was a little longer than I hoped for, but we've got it. So please come in with any questions that you have for me. We will be ready to work, and we will get this done tomorrow. And Patriots, I will see you when I see you, and I hope you have an absolutely great day.